About math. All right, let us begin with a word of prayer. Dear Heavenly Father, we thank you for the break which is about to start. Help us to get through this time and to do something profitable with it. In your name I pray, Lord Jesus. Amen. Yeah, I'm a little low energy at the moment, but I will get through it. All right, so let's start with a standard result. So this example, I'll call it an example, but it's really more of a theorem. And here it is, integral from 1 to infinity of dx over x to the power p is equal to the following. It's infinity if p is less than or equal to 1, and it is something else if if p is greater than 1. We'll figure out what goes in the blank here as we do the proof calculation, really. Okay. Now, just to give you a sense of why that would be, so for example, p less than, if p was equal to, for example, minus 1, then this would give you like dx over x to the minus 1, which would be the integral of x dx, right? And it's not hard to understand why that should be infinity, right? That's like not surprising at all, right? Because x keeps getting bigger and bigger and bigger. Why should the area under that be bounded? There's hope when what? It's a little bit ambiguous when p is between 0 and 1, right? Things like 1 over x or 1 over the square root of x, those things require a little bit more thinking. Anyway, so here it goes. So shall we do the general case first or the special case first? Let's do the special case first. If p equals to 1, what happens? We're looking at dx over x, right? And so that, by definition, is the limit. T goes to infinity. And what's integral from 1 to t? Dx over x. But you know what that is. That's the limit as t goes to infinity of the natural log of the absolute value of t minus the natural log of the absolute value of 1. Of course, the absolute values here are a little bit unneeded. And of course, what happens here, natural log of 1 is 0. Natural log of t, yeah. Okay, so that's infinity, right? Because this blows up. Right? All right, one case down, infinitely more to go. Right? So let's do them. On the other hand, if p is not equal to 1, well, all of those have the same antiderivative. They just require slightly different analysis. Integral from 1 to infinity of dx over x to the p is equal to, let me just rewrite this just a bit. I'm doing the definition of improper integration. Integral from t to infinity, t goes to infinity. Integral from 1 to t. And I'm going to rewrite that as x to the minus p power, right, dx. I think that would be helpful for us to do that. And then this is the limit as t goes to infinity. And what's my antiderivative? It is x to the 1 minus p over 1 minus p evaluated from 1 to t. So I added 1, right, and divided by the same thing. That's anti-differentiation. That makes sense because p is not equal to 1. See, p equals 1 is very special. Now, oh, by the way, is the audio bouncing? La 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 la. Yep. All right, exciting. Let's see here. So limit. I can't remember if I turned the thing on again. Limit as t goes to infinity, and then I got to evaluate this thing. What do I got? I got like t to the 1 minus p over 1 minus p, right? And then what? Minus 1 over 1 minus p. And then we have to break into cases, all right? Think about it. What happens if you have t to the 1 minus p, 1 minus p is fixed, right? What happens if t is a positive power? Like, what if you have t to the 0.25 power? As t goes to infinity, what happens to t to the 0.25 power? What's the fourth? In other words, like, what's the fourth root of a million? It's still a pretty big number, right? What's the fourth root of a kabillion? That's not a real number. You can't ask me that question. The point is, any positive power will go to infinity, right? And if you think about it, how about when you could have what? P. You can't get the 0 power because that's p equals to 1. It's not allowed. Right? So this is either what? Either we have 1 minus p is greater than 0, or we have 1 minus p is less than 0. Those are the two cases. If 1 minus p is greater than 0, you get infinity, right? Because that goes to infinity. If 1 minus p is less than 0, what happens is really that if 1 minus p is less than 0, that means t to the 1 minus p is equal to 1 over t to the p minus 1, right? What can you say about p minus 1 in this case? Right? P minus 1 is greater than 0 in this case. And so you've got like 1 over something that's getting huge as t goes to infinity. That goes to 0, right? I mean, the point is, but the whole thing isn't 0, is it? It's this, right? So it goes to minus 1 over 1 minus p in the other case. So, looks like I was right. See, because this we can repackage as what? In that kind of language, this is just what? P greater than 1, right? If I add p both sides, I get 1 is less than p, but that's the same as saying p is greater than 1. And so, to fill in the blank, we actually have 1 over, looks like, p minus 1. Any questions? So I know there's some cases to work out here, right? But this is something you really should be able to reproduce on your own if you were asked, right? I mean, I would not enjoy grading it, but it's not outside of the realm of, possibility that I would ask you this. Let's see here. So this is wonderful because it gives us like a standard lexicon, a sort of standard benchmark, a bunch of integrals that we know how they converge or diverge, right? Now, there's these things called comparison theorems, which are useful when you have something to compare to. And we do now, right? Comparison theorem. One of the comparison theorems is this. Let's see, I think it goes, I better get my book. I don't trust myself. I will leave out something important. Here we go. Suppose, I would have forgot to tell you that f and g are supposed to be continuous. That's important. Suppose f and g are continuous. All right. And 0 is less than or equal to f of x, is less than or equal to g of x for x in the ray that starts at a and goes to infinity, the interval from a to infinity, all right? Then you get two results. Let's see here. First result, 1, if the integral from a to infinity of g of x dx converges, which means what? What does it mean to say the integral converges? The limit which defines the integral actually converges to a real number, right? Like converges to infinity is not, I mean, we should say diverges to infinity, right? All right, so if that, then what? Intuitively, what do you think I should be able to say? What does this mean geometrically, that picture? It means like, if this is A, right? This is y equals f of x, right? And then above it, right, you've got, I mean, they can do like that, you know. But anyway, y equals g of x. So if the area under the red curve is finite, certainly the area under the purple curve should also be finite, right? That's the comparison test. So if this converges, then the integral from a to infinity of f of x dx converges. And then 2, right? If the integral from a to infinity, come on, I can't draw infinity, of f of x diverges. In other words, if the smaller one blows up, then the integral from a to infinity of g of x likewise diverges. Right? I mean, these are very, very natural theorems, right? And they're tricky to use, though. Not because they're really tricky, but because you guys, a lot of you lack confidence about how to do inequalities. I know I did when I was taking this class, right? We just don't do enough inequalities in our math education, so I think it doesn't get drummed into you guys like pretty much everybody can solve a quadratic equation, right? Because we've spent a stupid amount of time on that topic, but not as much on inequalities. Because it's painful, because we know people don't understand inequalities, so we don't want to come back to it, right? You guys don't want to spend time about what you don't know, right? But see, that's exactly the wrong idea. You should spend all of your time on the thing you don't know. That's how to get better, right? If you've got one super muscular arm, you should probably work out the other one, right? Unless it's just your goal to have like one like stupidly muscular arm, I don't know. I guess that could be. There is a little bit more you can say here. For part 1, you can also say this. The integral from a to infinity of f of x dx is less than or equal to the integral from a to infinity of g of x dx. You also get that. There's a pecking order. And zeros below them for what it's worth, because we assume that. That 0 is important. Without that 0 there's nothing saying that f of x couldn't be like way, way down there and have a divergent negative integral. Let me show you how this works. So we've got this like standard example to work with, example 1, right? And so if we look at examples similar, then we can use, if I make my example right, we'll see. I'm going to try. The verdict's out as to whether or not I can actually make this go. How about integral from 1 to infinity, I don't know, dx over x cubed. Now, I don't know if I want to do, let me think about this for a second. Yeah. Plus 1. You can put any number you want here. Let's see here. So check it out. F of x equals to 1 over x cubed plus 1, right? What is this less than? Right? That's what we want, but what is the g? Yes, it is less than g of x. I mean, that's just name calling, though. And nothing wrong with name calling. In fact, I encourage name calling here. Math is all about name calling, in fact. We're very interested in stereotypes. We really want to call everything the same thing if it's got the same properties. Oh man, what a violation of authenticity and individualism and all that good stuff. I mean, if you really think about it, mathematics is really an anathema to a modern, squishy-minded culture. X cubed plus 1, like that's true? Yes, no? Is it like a little bit true? I guess it depends on how you feel about it. I mean, is it... I mean, some people could say it's true, some people could say it's false. We can't really take a definitive statement one way or the other, you know? I mean, you just gotta, we have to agree to disagree.
Well, what makes it seem that it's false?
Let's see here. Is this true?
Since you're talking about it as a positive.
I think this should be smaller, right? Because we've added something to the denominator, which makes it a smaller fraction, right? Now this is what? This is p equals 3 in example 1, right? What do we know about p equals 3 in example 1? It converges. So, by comparison, the integral from 1 to infinity dx over x cubed plus 1 is less than or equal to the integral from 1 to infinity of dx over x cubed. And by the way, that is actually straight up equal to, we just calculated it, 1 over, what is that? 3 minus 1? Also known as 2? Yeah, so 1/2. Can any of you integrate 1 over x cubed plus 1 directly? If you have time? What u would you take? U equal to what? Tell me more.
X cubed plus 1.
U equals x cubed plus 1. Okay, so then du is 3x squared dx. So that's going to get me like integral of du over 3x squared divided by u. But I could solve for x squared, like x cubed is u minus 1, so that would make x squared u minus 1 to the 2/3. So this is really the integral of, like, you know, a du over 3 times u minus 1 to the 2/3 times u. Well, that's better. Maybe not. I mean, the thing about x cubed plus 1 is it's 0 if x is equal to 1, right? Minus 1, rather. So that means I can factor out x plus 1 from x cubed plus 1. By the factor theorem. I can do that much. This has got to be plus 1 over here. And Mr. King gave me a minus x. Let's see if I want to believe that. Does that work? I know that there has to be an x plus 1 factor out here because this is 0 when x is equal to minus 1, right? Factor theorem says there has to be an x plus 1 factor there. So x cubed minus x squared plus 1 plus x minus, yeah, it's good. Great, so 1 over x cubed plus 1 is equal to 1 over x plus 1, x squared, and that's irreducible. That's x minus 1/2 quantity squared, right? Plus 3/4, yeah. Oh, fine, so you partial fractions this thing. And so forth. After about a page of algebra, you got the antiderivative, and then you can take and calculate the integral directly, right? Or comparison theorem gives us a pretty good approximation with almost no work. Which do we like?
Comparison theorem.
Okay, I think I've made my point. All right. Any questions? Oh, when's our test? Tuesday after break? What did we cover? Oh, differential equations. That was the thing, right? Yeah, that's what it was.
It's a sign I'm saying now.
God saying don't do it. Spare them.
So I do owe you a take-home quiz, yeah. So I should give you a take-home quiz. It shouldn't take that long, really. It'd just be a few of these ones, mostly. Or do you want a take-home quiz which is more comprehensive? Comprehensive is better? All right, well, give me a few hours on that one. I'll try to have it for you later today, if I don't fall asleep first. Okie doke. Where was I? Yeah. Boring. How is that? Oh, right. This is a useful example. Check this out. Example 3. Integral from 1 to 4 of dx over x minus 2 squared. All right. Okay, so that is, let's see, the integral of 1 over x minus 2 is what? It's minus 1 over x minus 2. I take that, I evaluate from 1 to 4. I get minus 1 over what? 4 minus 2 plus 1 over 1 minus 2, which is what? Minus 1/2 minus 1 minus 3/2, right? What do you think? So guys, what do you have to tell me about this calculation I put on the board? What's that, Nathan? There's a discontinuity, so this is just nonsense, right? Now the one I did last class with the square root, if you had not written limits, you would have still gotten the right answer. Because it so happens that after we do the antiderivative, the limit is the same as just evaluating the antiderivative. It's a quirk of that example, but here, if you ignore the fact that there's a limiting process that's necessary, you get the wrong answer. This is in fact not true, what I have on the board. Because this has a volcano, right? This thing blows up at 2. Right? And so we're trying to find the area between, say, 1 and 4, right? And I like what this is as example 4 in the book, I think, or 5. I don't know. It's in your section. It's 11.7. But the book has one nice idea in here, really nice idea. I like it because it's nice and lazy. So that this is nonsense because I'm completely neglecting the fact that you can't just. The fundamental theorem of calculus part 2 only applies to continuous functions, or piecewise continuous functions with the proper jibber jabber. This is not that. This is an unbounded function, and we cannot just do that. It's not legit. So, but what the book's idea is, if you could show either half, if you can show either this, or either the left piece or the right piece diverges, that's it. You don't have to show both diverge, like I did in the example last class. Part of the reason I did that 4-part example last time was just to show you how the definition works. But in terms of just calculational clarity, if you have an integral that you have to break up into pieces, and one of the pieces, disconnected from the others, right, separately diverges to infinity, that's it. It is infinity. You don't need to calculate anything more. So like here, if I can show that the integral from, say, 2, well, let's say 1 to 2, 1 to 2 of dx over x minus 2, if I can show that that diverges, well, game over. That's it, you know? So this is the limit as, let's say, b goes to 2 from the left of the integral from 1 to b of dx over x minus 2 squared, which is equal to the limit as b goes to 2 from the left of, you know, minus 1 over x minus 2. I got to evaluate from 1 to b, which is the limit as b goes to 2 from the left of minus 1 over b minus 2 plus 1 over 1 minus 2. At this point, you know, we're done. Practically, all we have to do is just, you know, pick the fruit from the tree, so to speak. Let the apple fall to the ground. I mean, whatever you want to say. This is infinity, right? Because if we're approaching 2, b minus 2 goes to 0 in the denominator. There's nothing to stop it. It blows up. And so this in total is, I don't know if it's infinity. I guess it's infinity. I was debating whether it's plus or minus infinity, but it's graphically obvious that it's plus infinity, right? And so that implies that this is divergent. Geometrically, you can also see that the whole thing diverges to infinity, right? But if you had one piece that diverges to plus infinity and the other piece that diverges to minus infinity, these are disconnected, right, by the definition of the integral. So they can't cancel, right? So if you have like 1 plus infinity, 1 minus infinity, there's no hope of it being 0 in this kind of thing. They're just divergent. Let's try another comparison problem, see if I can't think of something for you guys. Oh, but first an application. You know, in quantum mechanics, we study something called a wave function. And the wave function is a probability density. So like, if you look at the wave function psi of x dx, well, it's not quite that. It's actually the modulus of this thing squared dx. This is like the probability of finding the particle, you know, in x plus, in the interval x to x plus dx, right? So, well, I'll stink. I guess I shouldn't talk about complex in here. Fine, I'll put it away. Anyway, so the integral from minus infinity to infinity of psi star psi, this should be equal to 1. This is the, what this says is the particle somewhere. So like the probability that the particle somewhere is given by this. So now in calculus, we shy away from complex stuff usually. So the sort of tamed down version of this you tend to see in calculus books is something like, prove f of x is a probability distribution. So f of x is actually like, this whole thing would be what your typical calculus book calls f. All right? And prove f of x is a probability distribution. What that means is that the integral from minus infinity to infinity of f of x dx is equal to 1. So like a very popular question, something like this. Where am I? What example am I on? What is it? Oh, I can't read. 4? Okay. So example 4. Choose a such that f of x equals to e to the a absolute value of x. E to the a absolute value of x is a probability distribution. Okay. Are you happy to find out that the test is about 60% differential equations and only about 40% chapter 11? Yes. Okay, I thought maybe. So, there's hope. There's hope. So what we need, right, is we need the integral from minus infinity to infinity of e to the a absolute value of x dx, which is what? This is really the integral from like minus infinity to 0 of e to the a absolute value of x dx, plus the integral from 0 to infinity of e to the a absolute value of x dx. Oops. Now, absolute value of x is a case-wise defined function, isn't it? So this is what? This is really the integral from minus infinity to 0 of e to the minus ax dx, right? Plus the integral from 0 to infinity of e to the what? Ax dx, yeah. For those of you who have intuition, it's bothering you I haven't written a minus in front of the a. Yes? Okay. That just means that a is going to be negative for this to make sense. Right? Anyway, so calculate. What do we got? We got limit as, let's say s goes to minus infinity of e to the, how does that go? I'll find an in-between step. E to the minus ax over minus a, right? Evaluated from s to 0, plus the limit as t goes to infinity of e to the ax over a, evaluated from 0 to t. Okay, what's that give me? Let's see here. So I've got minus 1 over a, right? Plus e to the minus as over a, plus the limit as t goes to infinity of e to the at over a minus 1 over a. How can I make both of these limits, converge? What do I need? If you look at this, right, s is going to minus infinity, right? So what's that mean about minus s is going to what? Plus infinity, right? So what does a have to be in order for that limit to exist? I mean, the only way that limit can exist is if it's 0, right? We know how exponential functions behave. It's either going to blow up to infinity or it's going to go to 0. We want it to go to 0. And to get that to go to 0, we need a to be less than 0. If a is less than 0, this goes to 0. If a is less than 0, this also goes to 0. Right? And what do we get? We get minus 1 over a, minus 1 over a, also known as minus 2 over a. Now that's supposed to equal to 1, right? If it's going to be a probability distribution, the net area under the thing has to be 1, and so you solve and you get a equals to what? Minus 2. So therefore, f of x equals to e to the minus 2 absolute value of x is a probability distribution. Here's another one we could do really quick. If I had f of x equals to a over 1 plus x squared, choose a to to make that a probability distribution. We worked that out the other day, remember? What was the integral from minus infinity to infinity of dx over x, 1 plus x squared? Pi over 2 is half of it. Pi over 2 is the other half of it. It's pi. So if that's equal to pi, you think for a second, and what's that tell you a has got to be? If I want that integral of f of x from minus infinity to infinity to be 1, we need a to be what? One over pi. We have a thinker. Yes. That's what I was looking for. Okay. You're like, could you put that one on the test, please? Right? Yeah. I might. I have before. I think at some point. A lot of people didn't get it. I think that's mostly because they didn't know what a probability distribution was. But I think I said so in the problem, though. I don't know. Once you throw an infinity in there, people get scared. It's weird. True, though. What's today? It's Wednesday. We still have 10 minutes, don't we? Yes, go ahead. Oh, just stretching? I'll allow it. Let's see here. Let's look at some more examples then. It is kind of wacky. You know, if you have the integral from 1 to infinity of dx over x to the 1.0000000, keep doing this the rest of your life, and then put a 1, you know, that converges. Right? And yet, the integral from 1 to infinity of dx over x to the 0.99999 da 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 da, the rest of your life, 8, you know, diverges. Isn't that weird? It's just such a change from such a small detail. Of course, 1 over x diverges, right? That's the breaking line, right? Let's see. How about what if I have integral from 1 to infinity? Let me make it 2 to infinity of dx over x times the log of x. Something I haven't emphasized enough in here is if something weird happens at the start of a sequence or at the start of an integral, you can just like throw it away and just focus on the tail behavior, like the end behavior. See, like here, it doesn't start, this doesn't start at 1, right? But while I stated example 1 for integrals starting at 1, it's pretty easy to see that there's a corresponding theorem for integrals that start at 2. In other words, to make this more formal, if I have the integral from a to infinity of f of x dx is less than infinity, then that implies that the integral from b to infinity of f of x dx is less than infinity for any b which is larger than a, right? Given the conditions, well, no, I mean, I'm supposing, of course, that a is, I guess, I don't know if a even has to be, I want to say a is positive, but I don't think I even really need to assume that. The point is I'm throwing away a finite value, a finite number of things which are convergent, you know, to get this. So if that behaves, then so does this. So the fact that I know that, I mean, I know, anyway, I'm not sure that helps us here. How about this one? I'm not sure I can compare in the right way this time. My intuition is that this might be convergent. I'm not sure. is 1 over, well, all 1 over x doesn't help me. How about this? 1 over, how does this relate to 1 over x? I need to check on that, right? Natural log of x for x larger than 2, what can you say about it? What's log x look like? Like that, right? Here's 1. Here's 2. So there's log x up here, right? Ooh, I guess the question is it, so what do you, I'm trying to think here how to say this. 1 over log x is what? Oh, that's complicated. Let me make it a little bit easier. Let me make this start at 3 so we can think easier. Otherwise, I got to do some thinking. I'm trying to avoid thinking at the moment. 3 is easier. Why? What's the natural log of 3? Well, what's the natural log of e? Natural log of e, by definition, essentially is 1. 3 is a little bit beyond that, so the natural log of 3 is a little bit bigger than 1. So it's fairly clear that the natural log of x is greater than 1 for x greater than 3. Right? It's up here. So if I wanted to throw away log x, would I make that fraction smaller or larger? My question to you is this less than 1 over x, or is this greater than 1 over x? Which is it? Less than. Right. So, what's this say about the comparison theorem? 1 over x. If you're comparing to 1 over x, what do you want? You don't want your function to be smaller than 1 over x. That's not helpful. Because 1 over x does what? Right? It's like, it's like you're in a hurricane and you pointed out that your roof is blown off, right? It doesn't mean that you're securely safe inside. It's not a good place to be if you're trying to stay in the house. Like this doesn't help me show that that's convergent, because this says, oh, it's smaller than something that diverges, right? So that doesn't really help me prove convergence or divergence, right? That's just useless as it relates to example 1. I think we can calculate this one directly, actually. How do you do this integral? I think if we let u equal to log x, right, then du is dx over x, right? So this is what? So we have integral of like dx. Let me do the antiderivative over here for just a second. X log x is actually what? This is actually the integral. This is kind of wacky. Check this out. It's du, right? That's the dx over x over u. So that, of course, is the natural log of the absolute value of u plus a constant, which is actually the natural log of the natural log of x plus a constant. Wacky, but true. So, in fact, this is the limit as t goes to infinity of the log of t minus the log of 3. Hey, I like the way that sounds. And so, bad news. Looks like we're getting sucked into the... Oh, I'm sorry, I shouldn't be talking about these things. There was a recent hurricane. I don't know, I do feel bad for the people in Haiti. I visited Haiti when I was a teenager. And even then, people say, oh, after the earthquake. It's like, it's got nothing to do with the earthquake. Like, Haiti has been a bad place to live long before there was an earthquake there. I mean, there's not a lot of places where you really have shelter from a hurricane. And so, I don't know. I wonder how that, I imagine that turned out badly. So I hope people are going to help. But Florida doesn't matter.
It went up the stage. It went up to Cat 4 today.
Florida?
Yeah.
Oh my.
Hitting the coast guard houses.
Ah. See, but with Florida would be okay. You know, we got houses and, I mean, it's just so much worse for a place like Haiti. Was there a question?
I was just gonna say, I have family there, but
In where?
my mom was in Haiti,
Oh,
and my mom was saying that like people were being pulled away by
I can imagine there's like, what, 20 inches of rain or something? I don't know. And there's no trees, right? Because there's the deforestation and everything. And I don't know, it's hard. Oh, so what happens with this? This is, that's just infinity, right? Log t blows up to infinity. So it's like something that's getting really big being fed to something else that's getting really big. So it's just bigly. So I'm sorry, that's the sort of thing I have to say. I'm trying to legitimize the verbiage of our dear leader. So future dear leader. Have you guys ever gone to the official website of North Korea? It is a lot of fun. There's like all these like essentially like worship of the leader of North Korea. It's surreal. Although I wonder, is that a real website that I went to? It seems like that'd be a really good joke. It's like my brother. I ever tell you about my brother's dream? His dream is of building a fake website to like, to bring to popular belief this McDonald's conspiracy. Do you know about the McDonald's conspiracy? They're everywhere. Like, you know, we can't get into North Korea, but there's a McDonald's in North Korea. You know, there's a McDonald's. You pick your favorite petty dictatorship. There's McDonald's there, right? They're everywhere, and you know they control. And blah, blah. I know I'm not as good as I used to be at explaining the McDonald's conspiracy. But my brother's dream was to build a website to really convince people of the McDonald's conspiracy, and then eventually for my mother to email him back about the McDonald's conspiracy. Then it would become full circle, and he would feel like he'd really accomplished something. I'm very fond of this idea. Never taken the time to really develop it properly, but it seems like fun. Anyway, so there's an example where comparison theorem doesn't help us, and we just have to calculate. So I don't know, it's a mixed bag, right? You have tools in your toolkit. Sometimes comparison theorem helps you. It really is a question of imagination. If you're actually asked to calculate the limit, comparison theorem at best puts an estimate on it, right? It doesn't tell you what it is. So, but that's useful, especially in chapter 12, we'll see. So, anyway, guys, have a good break. I'll try to get that quiz to you as soon as possible. Thanks.